This training module will introduce you to the working principle of Coriolis mass flow meters. A Coriolis meter is much more than a flow meter. It is also capable of measuring the density of the fluid. How is this possible? The double tubes are driven across a range of frequencies, and the electronics determine their resonance frequency, which is proportional to the oscillating mass. However, the amplitude is mostly unaffected. If the oscillating mass changes, the resonance frequency will change by the value of F. The oscillating mass consists of the tube mass and the fluid mass. The fluid mass corresponds directly to the density of the fluid, as the inner volume of the tubes is constant. The resonance frequency depends on a material constant of the tubes, which changes in case of varying temperatures. These effects are compensated by the electronics of the meter, thanks to the internal temperature measurement. In principle, no flow is required to enable a Coriolis meter to measure the density of a fluid. Coriolis meters are mainly used for liquids, but they can also be used for the measurement of gases or steam. It is, however, essential to understand major differences in the measurement. For liquids, the measurement of mass flow, density, volume flow, temperature, and concentration. For gases, however, Coriolis meters can only measure mass flow and temperature, nothing else. This is valid for all Coriolis meters from all manufacturers. The density measurement works, but the densities of gases are so small that the accuracy of density measurement is so limited that there is no usage thinkable. The accuracy level for mass flow is also different. For liquids, 0.1% is possible. For gases, 0.5% only. Some competitors can do 0.05% and 0.3%. If the gas density is known at a reference temperature and pressure, this density can be entered and a volume flow at these reference conditions can be calculated in the Coriolis meter. This is, however, just a fixed factor to the mass flow measurement. The basic principle of Coriolis metering also applies to single straight tube designs. Laws of physics dictate that straight tubes must be either very long or very thin in order to oscillate successfully. Bent tubes are much easier to drive in resonance frequency. In addition, straight tubes cannot expand under variable temperature conditions and therefore require a special material, titanium, which limits their temperature range. Often inquiries only request titanium because of the straight tube meter, even though there is no real technical need. The features of a single tube system are low pressure drop, sensitivity to noise including noise from outside vibrations, and noise from gas or solid contents. Single tube systems often use straight tubes, which means limited temperatures, below 100 degrees compared to 150 degrees. The features of a double tube system are a higher pressure drop than single tube designs, enhanced signal generation, and extremely high signal-to-noise ratio, which results in a higher accuracy level, and higher measurement dynamics, turn-down ratio. Insensitivity to noise, including noise from outside vibrations and noise from gas or solid contents. The tubes are often bent and are therefore much more flexible in case of temperature changes above 150 degrees. What have I learned so far? Mass flow is measured by the phase shift. The amplitude is mostly unaffected. Density measurement is based on the resonant frequency, and frequency depends directly on the density of the fluid. Temperature changes affect the frequency, and are therefore compensated by the electronics using internal temperature measurements. This compensation is possible because of the measurement of the tube fluid temperature.